June 7, 1940, Chrysler headquarters, Highland Park, Michigan. The telephone call lasted exactly 7 minutes, but those 7 minutes would fundamentally reshape modern warfare. William Knudsen, President Franklin Roosevelt's newly appointed Commissioner of Industrial Production, asked a question that seemed absurd at first glance. Can Chrysler build tanks? The man on the other end of the line, K.T. Keller, chief executive of the Chrysler Corporation, responded with brutal honesty. I don't know. I've never seen one of those things. At that moment, the United States Army possessed exactly 66 medium tanks. Nazi Germany had mobilized more than 3,000 panzers across Europe in little more than a year, crushing Poland in 26 days and France in 6 weeks through coordinated armored warfare. America's entire tank force could have been destroyed before lunch on any day of the Blitzkrieg. The mathematics of defeat were being written in blood on European battlefields. What neither Knudsen nor Keller knew was that their conversation would trigger the deepest industrial transformation in military history. In 9 months, Chrysler would achieve what military arsenals had never reached. Tanks, those 30-ton monsters that required months of labor from skilled craftsmen, would roll off assembly lines like automobiles, one every 55 minutes at the peak of production. The process would break all assumptions about military manufacturing and prove that American industrial genius could turn production itself into a weapon. The challenge began with a fundamental problem. In June 1940, the United States ranked 19th in military power, behind Portugal. The country's army had more horses than tanks. The Ordnance Department, responsible for weapons development, operated under production methods unchanged since World War I. Tanks were hand-assembled in government arsenals. Each was a custom creation that required specialized artisans. The Rock Island Arsenal in Illinois could produce perhaps 3 medium tanks per month, working at full capacity. Each tank took 12 weeks from raw material to battlefield readiness. Germany's Panzer production followed similar craft methods, but benefited from years of secret rearmament. In 1940, German manufacturers delivered 1,400 tanks annually across several factories. Britain, despite mechanizing faster than America, managed only 1,000 tanks annually. Every major military power saw tanks as sophisticated weapon systems that required master, craftsmen, specialized facilities, and months of careful assembly. Keller hung up the phone and immediately called his chief engineer, B.E. Hutchinson, along with Frank Zeter, Chrysler's vice president of engineering. The 3 men met in Keller's office in less than an hour. They faced an impossible proposal. The Army wanted 1,000 medium tanks. They wanted them in less than 18 months. And they wanted Chrysler to build a factory, design production methods, and deliver finished vehicles starting from absolute zero knowledge in tank manufacturing. Hutchinson's first question went straight to the heart of the problem. What is the current production time for a tank? Zeter had done his research. Rock Island Arsenal builds 3 M2A1 medium tanks per month, 12 weeks per unit. Skilled craftsmen throughout the process. Hand-fitted components. Hutchinson did the math immediately. At that rate, 1,000 tanks would require 277 years of production. The Army needed them in 18 months. Keller's response would define the entire program. We don't build tanks the Army way. We build them our way. If they want 1,000 tanks in 18 months, they need to accept automobile production methods, which means we need to see what we're building. Within days, the trio visited the Rock Island Arsenal. They observed while workers hand-fitted armor plates, adjusted track tension by eye and experience, and machined custom parts to compensate for tolerance variations. The current production model was the M2A1 medium tank, a 19-ton vehicle mounting a 37mm gun. Each tank required approximately 8,000 individual components, all manufactured with loose tolerances that required skilled fitting during assembly. No two tanks were identical. Keller recognized the fundamental problem immediately. This isn't manufacturing, it's sculpture. Each part depends on the skill of the craftsman. You can't scale this. You can't train new workers fast enough. And you certainly can't produce 1,000 tanks in 18 months. The trio returned to Detroit and convened what they called the Tank Committee, a secret working group that would solve the impossible problem. The committee included Owen Skelton, Chrysler's chief production engineer, along with specialists in tooling, metallurgy, and logistics. They worked in a requisitioned conference room at the Highland Park facility, meeting daily, often through the night. Their breakthrough came by reversing the fundamental question. Instead of asking how to build tanks faster, they asked how to build tanks differently. Skelton articulated the idea. An automobile has 2,000 pounds of steel, rubber, and glass assembled from 5,000 parts. We make 3,000 of them per day at Highland Park. A tank has 30,000 pounds of steel assembled from 8,000 parts. The only difference is what we are assembling. This reframing changed everything. If a tank was simply another mechanical assembly, then automobile production principles could be applied. But this required completely reimagining tank manufacturing from basic principles. Each component would need to be redesigned for mass production. Each assembly sequence would need to be re-engineered for line work, and each quality control step would need to change from the craftsman's judgment to measurable specifications. The committee analyzed the M2A1 design and discovered that 60% of production time was dedicated to custom fitting and adjustment. Parts manufactured according to military arsenal tolerances varied so much that assembly required constant adaptation. Hutchinson proposed the revolutionary solution. We manufacture every component according to automotive tolerances. Then, they fit together without adjustment. This seemed impossible to military engineers. Tank components faced stresses that exceeded those of automobile parts. Precision manufacturing in automotive tolerances would require new tooling, new suppliers, and new quality control methods. But the total production time would plummet. A tank that required 500 man-hours of assembly with manual adjustment could fall to perhaps 150 man-hours with precision components that would simply be bolted together. Skelton took the concept further. If we're treating this like automobile production, we need an assembly line, not a series of workstations where craftsmen gather around a stationary tank. A moving line that brings the work to stationary workers, each performing a specific operation. By November 1940, the committee had produced what they called the Chrysler method for tank production. Each major component would be manufactured with precision tolerances using automotive machine tools. Armor plates would be standardized and interchangeable. The hull would be welded using production jigs instead of being hand-fitted. The turret would be mounted on standardized rings. The powertrain would use as many existing automotive components as possible. And final assembly would take place on a moving line with specialized workstations. Keller presented the Chrysler method to the Army Ordnance Department in November 1940. Military engineers were skeptical, bordering on hostility. Automotive tolerances would be insufficiently robust for combat vehicles. Moving assembly lines would create quality control problems. Welded armor would be inferior to riveted construction, and the proposed production rate of 10 tanks per day was a fantasy. Keller had an irrefutable argument. You need 1,000 tanks in 18 months. We can deliver them. Can anyone else? The Ordnance Department could not answer that question affirmatively. In late November 1940, Chrysler received an unprecedented contract. The Army would pay for the construction of a purpose-built tank factory. Chrysler would design, equip, and operate the facility. The contract came with an additional requirement. The Army insisted that the new facility be designed by Albert Kahn, the Detroit architect who revolutionized factory design. Kahn's previous work included Ford's Highland Park plant and the River Rouge complex, facilities that allowed the mass production of automobiles on an unprecedented scale. Albert Kahn was 71 in 1940, a German Jewish immigrant who arrived in Detroit in 1881 at age 11. He never attended architecture school, learning his profession as an apprentice. In 1940, his firm, Albert Kahn Associates, employed 600 architects and engineers and had designed 19% of all architect-designed industrial factories in the United States. Kahn's genius lay in treating the factories themselves as machines. His designs maximized natural light, optimized material flow, and created column-free spaces that allowed for flexible production layouts. He pioneered the use of reinforced concrete, which allowed for larger open floors and faster construction than traditional steel frame buildings. When Keller approached Kahn about the tank arsenal in early July 1940, he presented requirements that seemed incompatible. The facility needed to be massive enough to house a complete tank assembly line plus component manufacturing. It needed to be built in months to meet the April deadline. It needed to be bomb-resistant, and it needed to be convertible for civilian production after the end of the war. Kahn accepted the commission and threw his entire firm into the problem. Teams worked 18 hours a day producing drawings for what would be called the Detroit Arsenal Tank Plant. The main building would measure 1,250,000 square feet under one roof, making it one of the largest industrial structures in the world. The design incorporated 3-foot-thick concrete walls in critical areas, thick enough to survive bomb impacts. The roof would be reinforced with steel trusses designed to deflect bomb blasts away from windows and ventilation systems. The layout of the facility incorporated the Chrysler method. A main assembly line would run the length of the building for almost a quarter of a mile. Feeder lines would bring main components to the main line at precise intervals. Machine shops would occupy the northern sections, producing powertrain components and precision parts. Welding bays would fill the southern sections, where armor hulls and turrets would be fabricated. The entire design allowed materials to flow in one direction, from raw steel at the west end to finished tanks rolling out the east. Kahn's plans included an innovation that military engineers had never considered. The assembly line would be sunken below floor level, creating a trench approximately 4 feet deep. Tanks would travel on special supports in this trench, allowing workers to access the underside without jacks or pits. This single design choice would save hundreds of hours per tank, making the installation of the suspension and powertrain much simpler. On September 9, 1940, the groundbreaking took place on 113 acres of former farmland in Warren Township, Michigan, just north of Detroit. The site was chosen for its proximity to existing Chrysler facilities and its access to rail lines. Construction began immediately and proceeded at a pace that seemed reckless. Several contractors worked simultaneously, racing to pour foundations, erect walls, and install utilities. Kahn's use of reinforced concrete allowed for rapid construction. Each section cured enough to support a load in a few days. In February 1941, the main building was structurally complete, but far from finished. The walls were up, but the windows were not installed. The roof was ready, but internal systems remained incomplete. Even so, Chrysler began moving equipment into the facility. Machine tools arrived by rail and were installed while construction continued around them. The most notable aspect was the schedule. Chrysler had committed to delivering the first tank by April 1941, but the factory would not be complete until May at the earliest. Keller made a decision that would become legendary. We will build the first tanks inside an unfinished building. This created bizarre working conditions that winter. Michigan's weather in February and March is brutally cold, with temperatures often below zero. The Detroit arsenal had walls and a roof, but no heating system installed yet, and the windows were still being placed. Workers assembled the tanks wearing heavy coats, with breath visible in the frigid air. The solution was improvised, but effective. A steam locomotive was brought inside the building, its boiler providing heat to the immediate work area. The image of a steam locomotive inside a factory building belching steam to warm workers who assembled tanks captures the absolute determination that drove the program. This was not careful planning. It was industrial will forcing reality to bend. Meanwhile, the tank committee solved technical challenges. The powertrain presented the first major obstacle. The M2A1 transmission was designed for manual assembly. Chrysler engineers redesigned it using automotive principles, creating a unit that could be assembled on a dedicated line and installed as a complete module. The redesign reduced assembly time from 40 hours to 4. The suspension system required a similar rethink. Chrysler engineers standardized each component and created fixtures that allowed for pre-assembly and testing before installation. A complete suspension bogie could now be built in 2 hours and bolted to the hull in 20 minutes. The iodized armored hull presented perhaps the greatest challenge. Traditional tank hulls were riveted from several plates, each rivet requiring manual drilling and installation. This process took weeks and created weakness, as rivets could shear off under impact, scattering deadly fragments inside the crew compartment. Chrysler proposed all-welded hulls. The Army objected vigorously. Welded armor had never been tested in combat. Welding created thermal stress that could compromise armor protection, and welding required skilled operators. Chrysler countered each objection methodically. They produced test welds that proved stronger than riveted joints under ballistic tests. They developed heat treatment processes that eliminated stress concerns. And they demonstrated that semi-skilled workers could produce acceptable welds after only 2 weeks of training using production jigs that positioned each piece perfectly. In March 1941, component production was underway. The tank that would roll out in TD-20 April would be assembled from parts manufactured in various Chrysler facilities and brought to Warren for final assembly. The engine situation required creative problem-solving. The M2A1 used the Continental R975 radial aircraft engine, a reliable power source that produced 400 horsepower. But Continental could not produce engines fast enough. Chrysler needed an alternative. The solution came from engineer Harry Wilson. Chrysler was developing a new inline 6-cylinder engine producing 115 horsepower. Wilson proposed combining 5 of these engines into a single power source. The concept seemed absurd. Linking 5 separate engines to drive a single output shaft created enormous engineering challenges. But Chrysler engineers loved challenging problems. Under Wilson's direction, they created what would become known as the A57 Multibank engine. The A57 used 5 complete inline 6-cylinder engines arranged in a circular pattern around a central gearbox. Each engine drove a gear that engaged a central output gear. The entire assembly produced 425 gross horsepower and 370 net horsepower from 30 cylinders displacing 1,253 cubic inches. It was bizarre, complex, and completely unprecedented. It was also brilliant. The multibank engine solved several problems simultaneously. It used existing tooling and components, allowing for immediate production. It did not require exotic materials or specialized manufacturing, and it could be assembled by relatively unskilled workers, following clear procedures. The Army hated it on principle, calling it a Rube Goldberg contraption, but they could not argue with the production schedule. April 12, 1941, one day before Easter Sunday, the Detroit Arsenal Tank Factory remained unfinished. Parts of the building lacked walls. Windows were missing everywhere. The heating system was still incomplete, but on the assembly line floor, the first M3 medium tank built by Chrysler was complete. The M3 represented an evolution of the M2A1, mounting a larger 75mm gun in a hull sponson and a 37mm gun in a fully rotating turret. The design was already obsolete, a compromise between proven technology and urgent need, but it was the first tank ever produced on an automobile-style assembly line. The formal delivery was marked with appropriate ceremony 12 days later. On April 24, 1941, the completed M3 was driven out of the still unfinished factory before a crowd of military officials, Chrysler executives, local, politicians, and workers. Keller rode on the tank as it emerged under the spring sun. The demonstration that followed was designed to impress skeptical military observers. The 28-ton M3 accelerated across the proving grounds, crushed obstacles, fired its weapons, and overall demonstrated that production methods had not compromised combat capability. A mock farm was obliterated when the tank drove straight through it. What the demonstration did not show was more significant. Behind that one, completed tank was a production system unlike anything the military world had ever seen. The assembly line was now operational. Component production was increasing. Supplier networks were being established, and hundreds of workers were learning their specialized tasks. May 1941 saw production increase to one tank every other day. In June, a tank rolled off the line daily. In July, 2 tanks a day became routine. Chrysler was simultaneously solving the supplier challenge. A single tank required approximately 8,000 components. Chrysler could not manufacture everything in-house. B.E. Hutchinson led the supplier development effort, traveling through Michigan and neighboring states. His pitch was direct. We need parts made to these specifications in these quantities on this schedule. Can you do it? Many suppliers recoiled at the demands, but Hutchinson offered something valuable in return: technical assistance, advance payment for tooling, and guaranteed contracts. The supplier network grew throughout 1941, eventually spanning more than 400 companies in 32 states. A foundry in Pennsylvania produced final drive housings. Machine shops in Wisconsin made track pins. A forge in Ohio supplied armor plates. The transformation of the workforce accompanied the development of the supply chain. In June 1940, Chrysler employed 0 workers with experience in tank manufacturing. In August 1941, the Detroit Arsenal employed 5,800 workers, most learning tank assembly from scratch. Chrysler established training schools where new workers learned specific operations before going to the production floor. A worker assigned to install transmission supports spent 2 days practicing on training jigs before touching a real tank. This allowed for rapid integration with minimal loss of productivity. In September 1941, the Detroit Arsenal was producing 4 tanks a day. The M3 medium tank was proving its worth in North Africa. British units receiving M3s under Lend-Lease nicknamed it the Key Grant after Ulysses S. Grant. They appreciated its reliability, though they criticized its high silhouette and the sponson-mounted main gun. Chrysler engineers were already working on the M3's replacement. The tank committee recognized from the beginning that the M3 was transitional. The sponson-mounted gun limited lateral movement and made the tank unnecessarily tall. A better design would mount the main gun in a fully rotating turret. Working with Army Ordnance engineers, Chrysler developed what would become the M4 Sherman, the most iconic American tank of World War II. The M4 used the basic hull and suspension of the M3, but mounted a 75mm gun in a rotating turret. The transition from M3 to M4 production demonstrated the flexibility of mass production. Instead of shutting down to change machinery, the Detroit Arsenal gradually introduced M4 components while finishing M3 contracts. By February 1942, the line produced only M4 Shermans. The M4 Sherman was designed from the idries, beginning for mass production. Chrysler engineers influenced every aspect of the design to maximize manufacturability. The hull used large castings or welded sections that required minimal manual fitting. The turret was cast as a single piece in specialized foundries. The powertrain used standardized components with interchangeable parts. Even the tracks were designed for rapid production. December 7, 1941, changed everything. The Japanese attack on Pearl Harbor brought America fully into World War II. The cautious ramp-up of production became a desperate race. The Army's tank requirements exploded overnight. The 1,000 tanks that seemed ambitious in 1940 became completely inadequate by 1942. Chrysler responded by accelerating production. The facility that had produced 4 tanks per day in September 1941 was producing 12 per day by March 1942. By July, 18 tanks daily rolled off the line. The production acceleration required solving countless problems. Bottlenecks appeared constantly, as different operations failed to keep pace. A shortage of qualified welders slowed hull production until Chrysler established welding schools that graduated 50 trained operators weekly. Machine tool availability limited component production until Chrysler arranged priority delivery. Owen Skelton, promoted to general manufacturing manager, established a system called production expediting. Teams of engineers monitored every operation on the production floor, identifying bottlenecks within hours and implementing fixes within days. The culture at the Detroit Arsenal became intensely focused on numbers. Daily production totals were posted prominently. Workers knew exactly how many tanks had been completed that day, that week, that month. Competition emerged between shifts, each trying to exceed the other's production totals. December 1942 saw the Detroit Arsenal achieve what many had claimed was impossible. In that single month, 896 Sherman tanks rolled off the assembly line and were delivered to the Army. This represented 29 tanks per day, a rate that exceeded all other American tank plants combined. The Detroit Arsenal alone was outproducing the entire German tank industry. The achievement came from relentless optimization. The assembly line now operated with mechanical precision. Tanks moved from station to station every 55 minutes. Workers had refined their operations through months of repetition. Suppliers delivered components with such reliability that inventory could be minimized. Quality control had evolved into a science, with inspectors checking dimensions and fit at every stage. The 896 tank month represented the peak of wartime production efficiency. While later months saw sustained high production, December 1942 remained the single-month record for the duration of the war. It demonstrated that tank production had been transformed from craft to industry. The Detroit Arsenal's success created demands for its replication. The Army wanted more tank production capacity distributed geographically. Several additional tank plants were constructed, including facilities operated by General Motors, Pressed Steel Car Company, and Pacific Car and Foundry. Each plant adopted the assembly line approach and precision manufacturing methods, but the Detroit arsenal remained unique in its production volume and efficiency. By the war's end in August 1945, the facility had produced 22,234 tanks of various models. This represented approximately 25% of all tanks built in the United States during World War II. The tanks themselves evolved continuously. The Sherman went through multiple variants, each incorporating improvements. The M4A1 featured a cast hull. The M4A2 used twin diesel engines for improved fuel efficiency in British and Soviet service. The M4A3 mounted the Ford Gvi-8 engine. The M4A4 used the Chrysler A57 Multibank engine. Each variant required production line modifications, yet the basic assembly process remained constant. This flexibility was another advantage. Craftsman production required rebuilding skills for each design change. Assembly line production simply required modifying fixtures and updating work instructions. The Sherman's reputation has been debated endlessly. It was inferior to German tanks like the Tiger and Panther in armor protection and firepower. Sherman crews faced terrifying odds in direct combat with these heavier vehicles. But the Sherman had advantages that mattered more in the aggregate. It was reliable, maintaining operational readiness far better than German tanks. It was easy to repair with standardized components and well-trained maintenance crews, and above all, it was available in overwhelming numbers. The production mathematics told the strategic story. Germany produced approximately 24,000 main battle tanks from 1939 to 1945. The Soviet Union built approximately 105,000 tanks in the same period. Britain managed about 28,000. The United States, entering large-scale production in 1942, built approximately $88,000 to 90,000 tanks by 1945. The Detroit arsenal alone produced roughly 1/4 of American output. But numbers tell only part of the story. The real transformation was in how tanks were produced. Before 1940, every major power treated tank manufacturing as specialized military work, requiring years of experience and government arsenals. After the Detroit arsenal, tank production was understood as industrial work, requiring engineering skill and production expertise. This philosophical shift had profound implications. It meant production could be scaled rapidly by engaging private industry. It meant workers could be trained in weeks rather than years. It meant supply chains could be distributed across entire continents. And it meant production capacity could be maintained even as experienced workers entered military service. After World War II ended, Chrysler continued operating the Detroit arsenal under government contract. Tank production ceased temporarily, but resumed with the Korean War. From 1952 to 1954, the facility produced 3,143 M47 Patton tanks. During the 1960s, it manufactured M60 tanks. In 1979, it began producing components for the M1 Abrams. In 1982, facing financial pressure, Chrysler sold its defense division to General Dynamics for $336 million. General Dynamics continued tank production at the arsenal until 1996, when consolidation shifted operations to the Lima Army Tank Plant in Ohio. The ID Detroit Arsenal site today hosts the United States Army TCOM Life Cycle Management Command and the Combat Capabilities Development Command Ground Vehicle Systems Center. A Michigan historical marker commemorates the site's role, noting that it produced more than 22,000 tanks and proved that American industrial might could be weaponized. The story's key figures went on to varying fates. Kaufman Thuma Keller continued leading Chrysler through the war years, becoming chairman in 1950. He retired in 1956. Albert Kahn died on December 8, 1942, just months after the Detroit Arsenal reached peak production. His architectural innovations influenced industrial construction throughout the 20th century. William Knudsen served throughout the war as a lieutenant general in the United States Army. Commissioned January 28, 1942, it was the highest rank ever given to someone not already in military service. He died in 1948. The Sherman tanks built at Detroit Arsenal served in every theater of World War II. They landed on Normandy beaches on D-Day. They fought across France and Germany. They island-hopped through the Pacific with Marine Corps units. They served in British, Canadian, Free French, Soviet, and Chinese armies under Lend-Lease. Many Shermans survived the war and continued in service for decades. Israel used modified Shermans in the 1967 Six-Day War and the 1973 Yom Kippur War. South American nations operated Shermans into the 1980s. A few remain in running condition today, preserved as monuments to an era when industrial capacity determined military power. The transformation of tank manufacturing from craft to industry happened because a handful of engineers and industrialists refused to accept conventional wisdom. They saw no fundamental difference between assembling an automobile and assembling a tank. Both were mechanical devices built from thousands of components. Both could be manufactured on moving assembly lines by specialized workers performing specific operations. This insight, simple in retrospect, was revolutionary in 1940. It required looking past surface differences to see underlying similarities. It required engineering courage to redesign military equipment despite military resistance, and it required industrial confidence to commit to production methods that had never been attempted at such scale. The success of the Detroit Arsenal validated Henry Ford's earlier insights about mass production while extending them into new domains. Ford had proved that interchangeable parts and moving assembly lines could produce automobiles at unprecedented volume and low cost. Chrysler proved these methods could produce instruments of war with equal efficiency. This possibility transformed World War II's outcome. Without mass-produced tanks, American ground forces would have fought at a severe numerical disadvantage. Britain would have struggled to replace losses. The Soviet Union benefited from thousands of American-made Shermans. The ability to produce 88,000 to 90,000 tanks in 4 years was unique to American industrial capacity, and roughly a quarter came from a single facility in Warren, Michigan. The invisible achievement was perhaps greater than the visible one. The Detroit Arsenal didn't just build tanks. It proved a concept. It demonstrated that private industry could solve government problems faster and more efficiently than the government could solve them itself. It showed that engineering expertise mattered more than military tradition. It validated the idea that American industrial capacity, if properly mobilized, represented a war-winning advantage. This validation shaped post-war American strategy. The concept of maintaining industrial capacity that could be rapidly converted to military production became central to Cold War planning. The idea that American industry could outproduce any potential adversary became doctrine, and the relationship between private contractors and military procurement that began with the Detroit Arsenal contract became a permanent structure. The engineers who made the Detroit Arsenal possible were practicing systems thinking before the term existed. They didn't just solve individual problems, they designed an entire system where components, suppliers, workers, assembly processes, and quality control functioned as an integrated whole. Each element was optimized not in isolation, but as part of the larger production system. This systems approach was visible in countless details. The assembly line's sunken trench eliminated a bottleneck in undercarriage assembly. The supplier network created resilience by distributing production across geography and multiple companies. The training system created a pipeline of skilled labor that could replace losses and support expansion. Every element was designed to scale. When production needed to double, the system could absorb that increase by adding shifts, expanding supplier orders, and training more workers. When new tank variants were introduced, the system could adapt by modifying fixtures and updating procedures. The ultimate measure of success was efficiency improvement over time. The first M3 tank, built in April 1941, required approximately 500 man-hours of labor. By December 1942, M4 Shermans were being built in approximately 150 man-hours. This productivity improvement of more than 300% came from continuous optimization. Every month, engineers studied production data, identifying operations, taking too long, or producing defects. They analyzed why workers struggled with particular tasks and redesigned fixtures or procedures. They questioned every decision, asking whether there was a faster, simpler, better way. This culture of continuous improvement, borrowed from civilian automotive production, was alien to military arsenals, accustomed to unchanging procedures, but it was essential to achieving the production volumes that the war demanded. The financial cost was substantial, but modest compared to output. The facility's initial construction cost approximately $20 million. Equipment and tooling added another $30 million. By the war's end, total investment exceeded $100 million. But the 22,234 tanks produced represented a value exceeding $2 billion. The return on investment was enormous by any measure. More significant than financial return was strategic value. The Detroit Arsenal's production capacity allowed American ground forces to fight with numerical superiority in armored vehicles. This advantage was crucial in campaigns from North Africa to Germany. Without the production capacity created at the Detroit Arsenal and similar facilities, World War II's outcome might have been very different. The story of the Detroit Arsenal is ultimately about seeing possibilities others missed. When Keller told Knudsen he had never seen one of these things, he was acknowledging ignorance, but not inability. Chrysler's engineers didn't know how to build tanks, but they knew how to build complicated mechanical assemblies from thousands of components. This confidence that engineering could solve any production problem was characteristically American. European manufacturers accepted that tanks were inherently different from civilian products, requiring specialized facilities and craftsman skills. American industrialists saw only machines, all of which could be broken down into components, processes, and assembly sequences. The Detroit Arsenal validated this philosophy completely. In 9 months, Chrysler went from zero tank production to delivering finished vehicles. In 18 months, they were producing tanks at rates that exceeded requirements. In 3 years, they had delivered more tanks than most nations produced in the entire war. The engineers and workers who made this achievement possible were ordinary people doing extraordinary work. They weren't heroes in the conventional sense. They didn't storm beaches or liberate concentration camps, but they built the tools that made those achievements possible. This democratization of military production was itself revolutionary. In previous wars, weapons came from specialized arsenals operated by master craftsmen. Production was limited by the availability of skilled labor. In World War II, American weapons came from automobile factories and dozens of civilian industries that converted to military production. The workers were housewives, recent high school graduates, farmers, and shop clerks who learned specific operations and performed them repeatedly. The Detroit Arsenal was the symbol and proof of this transformation. It showed that private industry could build military equipment more efficiently than government arsenals. It demonstrated that production methods developed for civilian goods could apply to weapons of war. It validated the arsenal of democracy concept, and it established that in modern warfare, industrial capacity was as important as military strategy. Today, most people driving past the site have no idea what happened there, but the legacy persists in less visible ways. The M1 Abrams tank is built using production methods descended directly from those developed at the Detroit Arsenal. Modern military manufacturing relies on private contractors using industrial production techniques. The integration of supplier networks, precision manufacturing, and assembly line production that Chrysler pioneered remains standard practice. The EV transformation from craft to industry that began on those 113 acres in Warren, Michigan, fundamentally changed how nations equipped their militaries. It proved that engineering expertise could solve seemingly impossible problems by refusing to accept conventional limitations. It showed that production principles could apply to the most complex military equipment. And it demonstrated that American industrial capacity, when properly mobilized, could produce the tools of victory in quantities that overwhelmed any adversary. This was the invisible weapon that helped win World War II. Not superior technology, or better tactics, or more resources, though all those mattered. The decisive advantage was the ability to treat war as an industrial problem and solve it with industrial methods. Kaufman Thuma Keller, answering that telephone call on June 7, 1940, couldn't have imagined where his honest admission would lead, but in saying he didn't know but would figure it out, he articulated the confidence that made victory possible. The engineers who designed the production system, the workers who operated it, and the suppliers who fed it were all engaged in a collective achievement that changed warfare itself. They proved that tanks could roll off assembly lines like cars. They showed that complexity was no barrier to mass production, and they demonstrated that American industrial genius, when challenged, could accomplish what military tradition said was impossible. The story deserves to be remembered not just for what was produced, but for how production was transformed. The Detroit Arsenal wasn't just a tank factory. It was proof that engineering thinking could solve any problem if the right people asked the right questions and refused to accept that impossible meant anything more than not tried yet. The tanks are mostly gone now, scrapped or preserved in museums. The factory has been largely demolished. The workers have passed away, but the method remains. The insight that complicated mechanical assemblies can be mass-produced, regardless of their intended purpose, survives in every modern factory. And the confidence that engineering can solve production problems lives on in every industrial designer who looks at a complicated product and asks, not can we build it, but how can we build it efficiently, reliably, and at scale? That question, asked and answered at the Detroit Arsenal between 1940 and 1945, changed the world. It made mass-produced warfare possible. It validated American industrial methods as superior to European craft traditions. It proved that private industry could outproduce government arsenals. And it showed that when engineers are given impossible problems, they sometimes solve them by refusing to recognize the impossibility. This is why the story matters. Not because tanks are interesting, though they are. Not because World War II is important, though it was, but because the Detroit Arsenal represents a way of thinking about problems that remains powerful today. See the underlying similarities, not the surface differences. Apply proven methods to new domains, design systems, not just components. And never accept that something can't be done just because it hasn't been done before. In 9 months, Chrysler went from never having seen a tank to producing them on assembly lines. In 18 months, they were exceeding all expectations. In 4 years, they built more tanks than most nations produced in the entire war. This was possible because engineers looked at a military problem and saw an industrial challenge. They refused to be constrained by tradition, convention, or pessimism. They solved the problem that remains the most important legacy. Not the tanks it built, but the proof it provided that engineering confidence, industrial capability, and systematic thinking can accomplish what seems impossible. When someone says it can't be done, the right answer is often, "Show me why not, and let's figure it out." That answer, applied consistently and confidently, built an arsenal that helped save democracy.